All right, so just quickly to remind you where we were at the end of last class, we want to implement a stack data structure. This time, instead of using an array, we want to use a bunch of linked nodes. So we need to define in C, you have to define a structure for the nodes. Right? So remember, we want to construct our stack using, we're going to use a struct of node, where each structure holds an element, and it holds a pointer to the next node in the stack. Right? So if that's a stack of size 1, where it's showing you the top element of the stack, the 1, that's your element. Right? Your arrow, that's your link. So that's going to be a pointer in this case. Right? If you want to push an element onto the stack, you make a new node. Right? You set the element in the node, and then you hook up the node to the next node, or to the current top node in the stack. Right? And then you adjust your top pointer so that it points to the newly created node. Right? And then, of course, if you're keeping track of the size of the stack, you add 1 to the stack size. Right? Now, when you pop an element, you're always popping the top element from the stack. Right? So when we pop off the stack, we're going to remove that 3. Right? So to remove the 3, we're going to remember what's the value stored in the node. Right? We're going to make our top pointer point to the next element in the node. Right? To get to that node, you're going to follow that link right there. Right? You're going to subtract 1 from the stack size, and then you're going to return the value that was in the node that you just popped. Right? All right, so let's take a look at the source code. The source code is on OnQ. So if you look at the lectures page, you can find a little zip file that contains the source code for this class, for this data structure. All right, so in our header file, right, we've got our usual include guard. Right? We've got our include of standard bool so that I can use true and false. And there's our type def for our structure. Right? So we're going to make a structure called lstack, and that's going to be our linked stack implementation. Right? Just like with the list, the definition of the structure is not here. Right? It's inside of the lstack source code file. Right? So people who are using this data structure, they don't know what the contents of this structure are. Right? All right, so the first function is a function that returns a pointer to a new empty stack. Right? If you think about Java, then this is analogous to a Java constructor that makes an empty stack. Right? So it would be equivalent to a no argument constructor in Java. This function here returns true if the stack pointed at by S is empty, and returns false otherwise. Right? Notice it's const. Right? So remember when a function says, or when a function has an argument or a parameter that's marked as const, right? Then the function is basically saying the function promises not to modify the stack using this pointer. Right? So in other words, this particular function is not going to, it won't add or remove nodes in the stack. It won't edit nodes in the stack, so it won't change the elements in the nodes. And it won't use push or pop. Right? The next function here returns the size of the stack, right? Number of elements in the stack. There's push. Right? So push pushes that element onto the top of that stack, or I guess the stack that's pointed at by S. Right? This S here is not const, right? Because we have to modify the stack, or this function has to modify the stack structure. Pop removes the top element off that stack. Right? And again, not const, because pop has to modify the stack in order to remove an element from the top of the stack. Oh, push returns true if it successfully pushes the element onto the stack, and false otherwise. Right? The only way it can return false is if it fails to allocate memory for a node. Right? And then we have a print. So instead of doing toString for stack, I'm just going to print out the stack. I'm just going to have a function that prints the stack. Right? Because it's a lot easier to print the stack than it is to return a string corresponding to the stack. And then finally, we need a function that frees the stack. Do we actually need one in this case? Well, OK, so yeah, we're going to have a function that frees the stack in this case. All right, so let's look at the implementation. So inside the lstack source code file, right? You're going to include the header file. We now have to define our node structure. Right? So here's our type def for our node. Right? The actual node structure definition is right here. Right? So in this case, because this is just a stack of int, we can store each element in a node just as a plain old int. Right? And now we need a pointer to the next node in the sequence. Right? And so there's our pointer to the next node in the sequence. Right? So every node has a pointer to another node in it. Right? So for those of you who had the CISC124 lecture on Wednesday, right, it's exactly the same. The node class is basically this. Right? This is basically the equivalent of the node class. Right? Except here, this would, in Java, that would be a reference. In C, it's just a pointer. There's the definition of the stack structure itself. Right? So the stack holds a pointer to the top node. Right? It doesn't hold all of the nodes. Right? So it doesn't have an array of nodes. It doesn't have a list of nodes. Right? It just has a pointer to the top node. Right? Every node in the sequence will hold a pointer to the next node. Right? And it's convenient to keep track of the size. So we're going to keep track of the size as well in the structure. All right, so the function that returns a new empty stack, well, it returns a pointer to a new empty stack. So we need to make we're going to make a pointer to the stack that we're going to return, right? And of course, the pointer has to point at something. So I'm going to allocate memory for the stack, right, using malloc. Right? So I now have a pointer to a chunk of memory where I can put a stack in, or I can put a stack structure in. Right? So I can now go ahead and fill in that memory. Right? Now S is a pointer, right? So I can use S arrow top to access the member top in the structure. Right? It's an empty stack, so the top node, there is no top node. Right? So I can just make that null. Right? The size is just 0. And that's it, right? Because our structure only has the two members in it. So once I'm done that, I can return S. Right? So what you must not do here is you must not do something like this. Right? Sorry, I'll stack T equals dot top equals null. And dot size equals 0. And then return the address of T. Wow, my typing really sucks today. Okay, so don't do this, right? So whatever you do, don't do this, right? So our stack is just a structure, so you can go ahead and make a structure. Right? You don't have to make a pointer to one. I can just make a structure, right? And I can set top to null, and I can set size to 0, right? And then you might mistakenly return the address of that structure, right? Because this function returns a pointer, right? So whatever you do, don't do that because, right, this thing here has automatic storage, right? It's a local variable, so it doesn't exist once or the memory for the variable does not exist after the function returns. Right? So if you return a pointer to that object, right, you're giving back the caller a pointer to something that doesn't exist. Right? So whatever you do, don't do that. So let me just comment that out. Right? If you want to return something back to the caller and that's guaranteed to exist after the function returns, you have to dynamically allocate memory for that thing. Right? So that's why we're using malloc here. Okay, is the stack empty? Yes.
If you go back up, what does a not S signify?
Is S null? Or is S not null in this? Sorry, if not, yes, is S null? Yeah. Right, so remember malloc can fail, right? So if malloc fails, it returns null. So you want to make sure that you don't want to return invalid memory back to the caller. Is the stack empty? That's easy, right? Is the size of the stack equal to 0? If it is, return true, otherwise return false. or just return s size equals 0. Right? To get the size of the stack, that's easy too, because we have a member inside the structure that records the size of the stack, so we just return that member. Right? Again, we're using the arrow here because we have a pointer to a stack, right? And not just the plain old structure, right? Not just a plain old stack. Okay, now what about, let's do pop first. Okay, so here's pop. So to pop the element off the stack, right, you're going to remember what is the value at the top of the stack, right? So that's these two lines here. Right? So I'm just going to remember what is the element currently in the top element of the stack, right? Step 2, you're going to adjust the top pointer of the stack so it points to the next element, right? So I'm going to adjust the top pointer of the stack so that it refers to or points at the next node in the sequence, right? So top is the top node of the sequence, right? Top.next or top arrow next in this case, that's just the second node in the sequence, right? And it's actually a pointer to the second node in the sequence. Right? So I can just set stop to point to that node. Right? Decrease the size of the stack by 1. Right? And now, don't forget to do this. Right? So when you push a node onto the stack, what you're going to do is, when you push an element onto the stack, you're going to make a new node, right? By allocating some memory for that node. Right? So when you pop an element off the stack, you have to deallocate the memory that was in that node, right? So if you forget to do this step here, right, the node that was pushed onto the stack, it never gets freed from memory, right? And if someone pushes and pops a whole bunch of elements onto the stack, they'll eventually run out of memory. Right? So you have to free that. Free the old top node, right? And then finally, you can return the element that you remembered back here in step 1. Right? Now, you're not allowed to pop an empty stack. Right? So to indicate that an error has occurred, oh, sorry, this is wrong. It's not supposed to return int. Does it return int? No, sorry, I'm being a dummy. It does return int. Never mind. To check if the stack is empty, we're just going to use assert. Right? So remember, assert's a condition. Right? So it makes sure that this thing here is true. Right? If it's true, the function goes on its merry way. If it's false, your program stops with an error. Right? So we're going to assert that the stack is not empty. Right? Not is empty. Right? So assert that the stack's not empty. If it's empty, the program crashes on that line. Right? Okay, and what about push? So for push, you're going to make a new node. Right? So we make a node. We test, right? Did malloc succeed, right? If it runs out of memory, it fails, right? If it fails, then we're going to return false. So this should probably never happen unless you really do have a situation where you do push so many elements on the stack that you run out of memory. The next thing we're going to do, we're going to fill in that node. Right? So remember, malloc gives you an uninitialized node, so we have to fill in the contents of the node. Right? So I want the element stored in the node to be equal to that. Right? I want to set the pointer to the next node, right, to equal the current top node in the stack. Right? So and this is S top, is that, right? So if that's our stack S, or that's the stack that's pointed to by S, right? And that's the current top of the node, right? Then what you want to do is you want to make a new node, right? So there's N, I'm calling it N, right? So that's N, right? We're going to put in the element that was pushed onto the node, onto the stack, into the node. Right? And now I need to hook N up to that. Right? So I need to set its next link, right, to point to this node. right? But that node is just pointed to by stop, right? So you can just write n next equals stop, right? And then of course, once you've done that, you've got a new top of the stack, right? So now you adjust stop so that it points at that node there, right? Which is just n. Increase the size of the stack by 1, and then return true to indicate that we successfully pushed an element onto the stack. Right? Okay, any questions about push or pop? All right. Printing a stack, I'm just, so it's, again, rather than return, oh wait, this actually is a good, there is a slide for this. Okay, so if I want to print a stack, I need to iterate over the nodes of the stack. Right? And that requires iterating over a linked sequence, right? Because we can't access the nodes by index, right? All we have is a is a pointer to the top node of the stack, right? So I have to iterate over the sequence of nodes. You know where to start, right? You're going to start at the top of the stack. You also know where to end because the stack, the last node of the stack, its next pointer is always null. Right? So you know how to start the iteration. Furthermore, you know how to stop the iteration. You just look for a null next link. Right? So there's a general pattern for iterating over these linked sequences. Right? So starting at some node, it might be the top node, it might be somewhere else. Right? You just get a pointer to the starting node. Right? And then while that node is not null, right? So while that pointer is not null, you can do something with n. Right? So n actually points at a node. Right? So I can access n.elem, or n arrow elem, right? I can access n arrow next, right? And then you can do right? So you do something with the node, or the contents of the node, and then advance the node, or advance n, so that it points at the next node, right? So n equals n arrow next, and that just moves n to the next node in the sequence, right? When you're done, right? When this loop exits, n is null. So whatever you do, don't dereference n at the end of that loop. Right? Because dereferencing a null pointer will ends up doing bad things. Right? So to print, so an example of this loop, right? Starting at the top. Whoops, sorry. Boop, boop, boop. Right? Is n null? The answer is no. So do something with the node, right? And then advance n, right? By following that link right there. Right? So that moves n to the next node. Right? Is n null? Well, no, it points at a node. Right? So do something with n and then advance it following that link there. Right? Is n null? The answer is no. Right? So do something with the node and then advance it following that link there. Now that link is null, but you're still allowed to set n to that node, to that link. Right? So you can still write n equals n next there. Right? Now n is null. Right? And so now the loop stops. Right? And so there's how you can print. So using that loop, you can easily print the nodes or print the elements in the nodes of a stack. Right? So you just start at the top. Right? While n is not null, do something with the node. So in this case, I'm going to get the element in the node and print it. Right? And then advance the pointer one forward, right? By following the next link. And that's it. So printing a stack is straightforward. Okay, so if you were in the 124 lecture, our node structure is an example of a recursive structure. Is an example of recursion of a structure. Well, it's a recursive structure, right? So every node has a pointer to a node, right? That node has a pointer to a node. That node has a pointer to a node, and so on and so on, right? Furthermore, every node in a stack can be viewed as the top of another stack, right? So our top of the stack is here, right? That node represents the top of the stack of size 3. But that second node here, that's the top of a stack of size 2, right? It's still a stack, right? It has 2 elements in it. That node there, that's the top of a stack of size 1, right? And so because the structure of of our stack is recursive, right? You can easily write a recursive algorithm that operates on nodes, right? So instead of writing that to print the stack, right? You can write the following to print a stack. Right? So here's the print. Here's the lstack print function. It's going to call print rec. So that's the recursive implementation of print. Right? So the recursive implementation of print takes in a node, right? So print recursive will print a stack whose top node is n. Right? So one more time, print recursive will print a stack or print the contents of a stack whose top node is n. All right, so if n is null, then there is no stack, right? So there's nothing to print, so we just return. So there's our base case in the recursive function. Right? If n's not null, right, then I'm going to print out whatever element is inside of n, and then I want to print the rest of the stack. Right? So print the element in n, well, that's easy. Right? Now, how do I print the rest of the stack? Well, the rest of the stack, right, the top element of the rest of the stack starts at n next. So I just recursively called the print rec, passing in n next as the node. Right? So in this example here, the first time you call the function, right, n is there, right? So that's so that's n there, right? The recursive call passes in that node, right? The recursive call for this passes in this node, and the recursive call for this passes in null, right? So you get the empty string, then whatever element is here, then whatever element is here, and then whatever element is there. Right? Sorry, I did that backwards. You get the element here, then the element here, then the element here, and then nothing, because that's null. Right? So the function that the caller would use is this one here, right? And then this function here just calls the recursive implementation of the function. Right? And so it's very easy to write recursive algorithms when you have these linked structures. Right? In CISC235, is anybody taking CISC235 right now? Or do you need this course before you? I don't know if you need this course. You need this one before 235? Is that true? I don't think that's true.
You need logic.
Oh, you need something else. Okay, so you're taking those other things. So CISC235, you're going to see more of these linked structures, but you're going to see different types of linked structures. You're going to see trees. So your nodes are going to look like this. You'll see structures that look like that, right? Or more complicated ones, right? And so writing iterative methods or functions on stacks or lists is normally what you want to do. But as soon as you have a structure like this, trying to write an iterative version of a function that works on that is a lot harder. And so if you can learn to think recursively on these linked structures, then dealing with CISC235 and writing algorithms on trees becomes a lot easier. Oh, sorry, yes, question.
What do you have to put? What do you have to set the type to be constant for the node?
What? Oh, why is it const?
Yeah.
Okay, so remember when a function takes in something that's const, the function is promising it's not going to modify, in this case, the stack that's pointed at by s, right? That's what it's saying, right? So this function never modifies s, right? That's actually important. If you're calling a function, you want to know, does that function modify the thing you're passing in, right? Yes?
Is it actually enforce that once you're actually writing the function?
Yes. So if you try, say here, right? So suppose inside my print function here, I call pop or push, right? Pop or push takes in a non-const stack, a pointer to a non-const pointer, right? So if you try to call that, the compiler will flag that as an error. Right? So inside, so if you actually try to modify s using push or pop here, right? The compiler will flag this immediately as an error, and it won't compile. Now, in C, you can cast away constants. So it is possible to write a function that takes in a const pointer and then throws it away and modifies the thing. Right? C will let you do whatever you want to do. Right? It says, look, whatever you write, that's what I'm going to do. Right? And I'm going to assume, and the compiler just assumes you're doing what you intend to do. Right? So you can, in fact, do things like cast away the constants of a pointer.
Is there ever a time where you would do that?
Sometimes you have to. There are occasions where usually it happens when you're not writing your own code, but you're working on someone else's code that's already been written. And then you realize that as you're updating their code, this thing that's const really can't be const. And you have to go ahead and cast it away. Right? So for example, you might have to temporarily modify this stack and then set it back to its original state. So logically it's constant, right? But when you actually go to implement it, you have to throw away the constantness in order to modify, then undo the modification. Yeah. All right. Any questions about implementing a stack with a linked sequence of nodes? Yes?
If you like flip the order of the printf and the print, will it like print it like backwards?
That's good. Yes, it will print it backwards. It will print it from bottom up. Yep. With just one change, yes. It's just changing the order of the lines. It'll print it the other way. Any other questions? All right. Same lecture almost, but slightly different. So the problem with our list and our stack is that the element type is fixed, right? So we have a list of int, we have a stack of int. So you went through all this trouble to make a list, right? And because lists are useful, and stacks are useful too, right? But you can only hold ints in our implementation, right? So if I wanted to change, or if I wanted a list that could hold something else, like strings, right? The only solution in C, if we're going to use our current solution, right, is to make an entirely new header and source code file for a list or a stack of string. And then basically copy over all of our code for int, and then modify wherever there's an int, I have to change it to a string, and then make some other changes, right? So it works with string. Right? And that kind of sucks, because then as soon as you need a list of double, you have to do the same thing, right? So this involves a lot of manual copying and code duplication. And the code duplication, you end up just changing a few types for the most part. Right? Now, the language C++, this is essentially what happens, right? So C++ has a mechanism called templates, which are analogous to Java generics. Right? So I can make in C++, you can make a class that's a list, and then you can specify the type of element you want in the list. Right? But the way it's implemented is it just copies your source code file and makes a separate copy of it for every type that you have. Right? So if you have a list of int, then you get somewhere there's a version of that source code file that represents a list of int. Somewhere else there's a version that represents a list of strings. Somewhere else there's a version that represents a list of double. Right? So C++ automates that copying and code duplication. Right? Now the templates actually do a lot more, which you will probably learn about later on. In Java generics, it doesn't work this way. Right? So in Java generics, what happens is you specify the generic type. Right? Your program compiles, right? And the compiler checks that you're using your list safely. Right? That is, when you add an int to a list, you get back an int when you take it out, right? And then it tosses out the generic type, right? So what actually happens is your list of string in Java is really a list of object at runtime, right? Similarly, your list of int or a list of integer in Java is really a list of object at runtime, right? So there is no code copying in Java. Java has a different way of implementing this. Now, in C, if we want to make a list or a stack that can hold any element type, we have a problem because there is no type that represents any element type. Right? So in other words, there's no universal type where I can store an int and a double and a string. Right? That just can't be done. What C does have, though, is it's got this pointer to void, or this void pointer. Right? And remember, a void pointer is allowed to point at anything. Right? And so what we can do is we can make a list or a stack where the elements are void pointers. Right? So they point at something. Right? So I have a pointer that can point at anything, and we're just going to point at the values that we want to store in the stack or list. Right? So there is, if you do this, right, what you end up with is a collection that resembles a Python-like collection, right, where you can put anything you want into the collection. Right? So in Python, if you make a list, you can put whatever you want in the list. Right? You can put in a double, then an int, then a string, and then whatever you want. Right? Another list, right? Which is different than in Java. Right? So you can do this in C, but you end up losing all type safety. Right? Whoever is using this list or stack, they're responsible for putting things in and taking them out and converting them back and forth properly. Right? So to implement a generic stack, it's not that difficult. Right? The structure itself doesn't really need to change. The stack structure itself doesn't need to change. Right? It's got a top pointer and it's got the size. Right? The node structure has to change. Right? So instead of having an int as the element type, I now have a pointer, a void pointer, right, where the pointer points at the element that we want to store in the stack. Right? The node pointer doesn't change. Right? So that's change number 1 right there. All right, if you go and look carefully at the stack implementation, oh, sorry, if the only thing that changes is this thing right here, right, that pointer, instead of storing elem as an int, we're storing it as a pointer, right? Then if you go and look at the source code for the stack, for our stack implementation, right, init is empty and size, right? None of those actually involve the element at all, right? So here's init, right? So we allocate memory for the stack, right? We set top and we set size. Top gets set to null, which, yeah, that's fine, right? But we never actually touch s top elem, right? Well, there is no s top elem, right? Because there is no node, right? So this one, we don't use nodes at all, right? Is empty, there's no reference to a node here. And size, there's no reference to a node here. So none of these change, right? So that's good, right? If you look a little bit deeper, right, then you'll realize that any function that takes in or returns an element, that has to change, right? So push used to take in an int as its element, right? So now it has to take in a pointer to void, right? Pop used to return an int, right, as its element. Now it has to return a pointer to void. So those changes are pretty straightforward too, right? But as soon as you look at print, you realize that there's a problem, right? So let's go look at print. So we look at print and we see, okay, so we're going to print out something here. That's great. We got a node. Okay, that's fine. And then right there is where you run into your problem, right? So for print, print uses printf to print the element, right? Printf needs to know the type of the element right there, right? So here in our int stack, right, we know that the element type is int. But if I have a generic stack, I don't know what that conversion specifier is. Right? More generally, I don't even know if I can use printf to print out the element type, right? Because if someone makes a stack and they push in a bunch of structures onto the stack, right, there's no way to print a structure in C, right? You need some function that's going to print the structure. So there's a problem. Right? Did I do free? Oh, free. Sorry, I forgot to tell you how to do free. So the free function is the function that deallocates the memory for the stack, right? Now remember when we made the stack and we pushed a bunch of elements on it, I allocated memory for that node, and that node, right? So when you free the memory associated with the stack, you have to deallocate the memory for that node, and that node, right? And that looks a lot like printing a stack, right? You have to iterate over the nodes in the stack, right? So once again, we're going to start at the top of the stack, right? While n is not null, right? I'm going to grab the next element first. So I'm going to, if that's n, then next is going to point to that node there, right? I'm then going to free n, right? So that memory associated with this node disappears, right? Its pointer is also invalid, right? Because I can't use n anything once I free it. That's why I had to get next first, right? And then I can set n equals the next, right? So I'm just going to iterate over the sequence of nodes, freeing the nodes as I go. And then at the end, I'm going to free the memory for the stack. But here, there's another problem, right? Sorry. So freeing the node here, there's no issue because we just have, our nodes are just, they hold an int in them, right? Where's the node? Up here, right? So the nodes, they have an int in it, right? And so when you free the memory for the node, the memory for the int goes away as well. As soon as we change, where's stack? Oops, sorry. Oh, okay, sorry. Okay. As soon as you change this to a generic stack, right? We now have the problem is when I free this node, right? Does the user want me to free the element, free the memory associated with the element, right? Because I no longer have an element. I've got a pointer to an element, right? So the question is does the user of the stack want me to free the memory associated with the element or not, right? If the answer is yes, right, then if the answer is yes, right, then there's a problem because I actually don't know how to free the memory associated with that element because I don't even know what it points at, right? If the answer is no, that's fine. Then our implementation works just fine, right? So we've got a couple of problems, right? Printing, I don't know how to print an element. For freeing a node, I don't necessarily know how to free the element that's stored in the node. So the way you solve this is by making the following observation, right? If I want to print something, that's just some algorithm, right? And if I want to free something, that's also just some algorithm, right? The algorithm might be complicated, but it's just an algorithm, right? So in C, an algorithm is just a function, right? So if I can somehow tell print or free, what function do I want to call when I print an element, or what function do I want to call when you free a node, right? Then we can actually implement the function, right? And so what we want is a mechanism to pass a function to another function, right? So the way this works in C is you can make a pointer to a function, right? All right, so I have a function of the following form, right? So that's your return type, right? So say int, right? That's the name of your function, f, right? You've got a bunch of parameters. It doesn't matter what they are, right? So that's the function that I want. If I want to make a pointer to this function, then the pointer to the function looks like the following. Now notice the pointer to the function looks really gross, right? It ends up looking like this. So you basically copy all of this, right? And then delete the function name, right? You replace the function name with round brackets, an asterisk, and the name of your pointer, right? So pointer name is the name of the variable, is the name of your variable that you want, right? So for example, it's a lot easier if you see an example for this. Here's my function do nothing, right? Its return value is void, and it has a void parameter. If I want to make a pointer to this function, then what I write is the following, right? So it returns void, right? It has void as its parameter, right? Round bracket, star, and then name of my variable, right? So that right there makes a pointer called ptr1 that I can use to point to a function that returns nothing and has no arguments or no parameters, right? And you can assign a value to that pointer by passing in the address of a function. The following also works. You can just write the function name as well, right? So ptr1 is a pointer to our do nothing function. All right, let's look at another example here. Here I've got a function that returns void, right? It has one parameter of type int. If I want a pointer to this function, right, I write void, so the return type. I write the types in the parameter list, right? So that's just int, right? And then I write the name of the pointer and an asterisk to indicate that it's a pointer, right? So ptr2 is a pointer to a function that returns void and has one int parameter, right? And I can make that pointer point at the function printint, right? Either by taking the address of printint or just writing printint, right? So that's fine too. Okay. Slightly more complicated example. Max computes the max of A and B and returns the max. So it returns an int, has two int parameters. Right? A pointer that can point at max would look like the following. Right? So returns int, has 2 int parameters, right? Star ptr3, right? So ptr3 is a pointer that points at a function that returns int, has 2 int parameters. I can make it point at the max function by passing in the address of max or just max. The next one. So this ptr4 is a pointer at a function that returns a pointer to a double and has 1 double parameter. Right? And apparently it's pointing at the make double function. So let's go look at make double. So make double allocates memory for a double value, sets its value to A, and then returns that double value. Not the most useful function here. It basically makes an array of size 1 that can store a double. Right? Now, you can have a pointer to a function that also takes in a pointer to a function. So this one here is particularly complicated. Right? So here's make int. Right? It takes in an int A, it takes in an int B, and what is this? Right? So that is, so fp is a pointer to a function that returns an int and takes in 2 ints as its arguments. Right? So it's a pointer to a function that takes in an int, has 2 int arguments. Right? So I'm going to allocate memory for an int. Right? So an array of size 1. I'm now going to call whatever function this points at. Right? So the way you call the function is like this. Right? So fp is a pointer, so I dereference the pointer. Right? That gives me a function, which I can call with a and b. Right? Alternatively, you are allowed to write star I equals, so you can just write fp here actually, a comma b. Right? So you, because it's a pointer to a function, the language doesn't force you to dereference the pointer. Right? You can just call, you can just use the pointer itself to call the function. So that's fine as well. Right? And then I can return I. Right? Now, why on earth would I want to do this? Right? So let's see what happens down here. So there's my function. Right? If I want a pointer, oops, sorry. If I want a pointer to that function, right, then you just copy all of this. Right? Get rid of the parameter names. Copy all of that. Copy that. Right? So there's my int star at the front. Right? Oh, I guess you're allowed to include the parameter names if you want. Right? Copy all of the parameter lists there. Right? Now ptr5 is a pointer to a function, to my make int function. Right? Now how do I call this function here? Right? So how do I call that function there? Right? So using ptr5, I can call make int by passing in 5 and 10. Right? And now I need a pointer to a function that takes in 2 ints and returns an int. Right? So here, I can pass in a pointer to max. Right? And so what x ends up being is 10 in this case here. Right? Because if you go back up to here, right, make int calls our function. So this is just max. Right? Computes the max of a and b, stores it in I. Right? So effectively, what this ends up doing is calling max with 5 and 10 and storing it in x. Right. Any questions? That last one is a bit complicated to follow. That last one is a little bit complicated to follow. Right? But if you just remember that that's just a pointer to a function, right? And then you realize that this thing here is just going to use that function to evaluate the return value. Right? That's all it's doing. Right? But you can pass in whatever function you want here. Right? So you can make another function min right there. Right? There's min. Right? Then instead of calling max, right, which is ptr, oh, ptr3 here is min. Sorry. So ptr3 right now is max. If you delete it and set it to min, it's min. Right? So by changing this pointer, or by changing the function that this points at, you can call another function. Right? And that turns out to be super useful when you go to implement your generic data structure. Right? So the print function for our stack is going to take in a pointer to a function that can print an element. Right? And that's how it's all going to work. All right. So to print an element, right, what I want to call a function, right, that takes in. Now remember, our elements are stored as pointers to void, right? So I want it to call a function that takes in a function, sorry, that takes in a pointer to void, right? That points at the element to print, right? So this function print element, the user is going to supply this function, right? So the user is going to make a stack. They're going to put in, say, a bunch of doubles, right? If they want to print the stack, then they need to give me a function that looks like something like this, right? And the version of their function will print a double, right? Then inside the stack implementation, we're going to use that pointer to the function to call their function to print the value, right? So if that's the function I want to call, then I want a pointer that looks like this, right? Returns nothing, right? Takes in a const void pointer, right? And there's just our pointer name. Right? Now, this isn't the most friendly thing in the world to look at, right? Especially if you're not used to looking at pointers to functions. So you can just use a type def and get rid of all this ugliness, right? So I can type def that, right? So type def void print elemfunc. That's going to be the name of my type def, right? So print elemfunc. That's just going to be the type now, right? And print elemfunc, that's a function, that's a pointer to a function that looks like that, right? So print elemfunc is an alias for a pointer to a function that has a const void star pointer that returns void. Right? To free an element, right, we want to call a function that looks like this, right? So free elem frees the element that's pointed at by this pointer here, right? So what does that mean? I need a pointer that looks like void and void star here, right? So again, you can type def that. So I can make a type def free elemfunc that is a pointer to a function that returns void and takes in a pointer to a void. It takes in pointer to void. Okay. So what does all of that look like when you put it together? So here's stack.h. This is going to be for our generic stack, right? There's our type def, right? So there's a pointer to a function that prints an element, right? So I'm going to make that type def usable or available to anybody who's going to use the stack, right? And there's free elemfunc. Right? Again, a pointer to a function that can free an element pointed at by that. Right? And I'll make that type def available to everybody too. Right? And then the rest of the class, the rest of the data structure is basically the same as the previous one. Right? There's init, there's is empty, there's size, there's push, there's pop. Right? Push now takes in a pointer to void. Pop now returns a pointer to void. Right? Print changes a little bit. Right? So print used to just take in a stack, right? But now it also takes in a pointer to a function that can print an element, right? Notice that that's a lot nicer to read, right, than the actual pointer itself, right? So it's way easier to read this, right? So once you see this, it's like, oh, they just want a pointer to a function, right? Similarly, free, instead of just freeing the stack, there's also a pointer to a function that can free an element. Right? Again, the type def for free elemfunc makes this a lot easier to read than just reading the original pointer to something that frees something. Right? All right, so we're out of time. I guess we'll look at the implementation in the next class.